So thank you very much for the kind introduction. Thank you, Jairo and Karine, to let me present my cooking recipes here for Skyrmions. So actually this is kind of a spin-off of Skyrmion à la carte talk, and you will see why. I will here focus more on the effect of frustration of exchange interaction and see how the way we model Skyrmion is actually resulting in spin glass kind of behavior. So of course there is a lot of collaborators who worked on this part, on this talk, and I always like to acknowledge everybody. So there is the group of Stefan Heinze in Kiel, where I worked for a long time, and I learned a lot there. We worked in very close collaboration with the group of Stefan Blügel in Jülich for the DFT calculations. More recently, we actually work with Jovan Kim, who is staying here for the summer. And there is a lot of part done with the University of Reykjavik. And of course, there is the group of Mainz, the group of Jairo Sinova. So this is what I'm going to talk about today. So very brief introduction on Skyrmions, because I think it was already introduced. Then we will see actually how we understand the system, and I will focus on this system, which will be the main focus on my talk, which is palladium, iron, iridium, and we will see how the DFT calculations that we do can understand and predict very well the stabilization of isolated skyrmions. We'll see that we can actually calculate from DFT the Dialogin-Skimoria interactions, and then based on these two steps, we can then obtain an extended Heisenberg Hamiltonian that then we can play with Monte Carlo and spin dynamic simulation. And then I will use this to focus on this part of the magnetic exchange frustration and its consequences, where we will see that we will look at energy barriers for the collapse of these topological protected spin structures, and also temperature dependence, so BT phase diagram. So first, very briefly, a very short introduction. So you have seen already, so Skyrmions are actually zero-dimensional objects. They are shown here. So they were predicted first in this paper in 1989. So that's the prediction that they might occur in materials. So you see that a skyrmion is actually composed of two things. So you have a ferromagnetic background here around, and then you have a core of the skyrmion. So the ferromagnetic background is pointing up, and the core is pointing down. And as you go from the ferromagnetic background to the core, wherever you are, the spins are always, or the magnetic moment are always rotating in the same directions. These objects are therefore called chiral. So they were first seen in these papers. So this is MNSI. They are also seen quite often in via Lorentz microscopy. And one of the interesting things that you can do with skyrmions is actually you can move them on ferromagnetic thin films, and the idea of this thing is to have racetrack based on isolated skyrmions. And as you can see, so this is a non-exhaustive set of papers. This is subject to actually very intense research. So you have seen here the anti-skyrmion in order to the skyrmion. In order to characterize this object, we calculate what is called the skyrmion number. We can also call it, depending on the community, the topological charge. And actually, it's a rather simple formula, which you see here. It's an integral, and it counts the number of times the magnetic moment is mapping a unisphere as you go across the skyrmion. So you see that you have a skyrmion here, which is the same picture as I've shown before, but it's a top view. So you have a ferromagnetic background, and as you go in the center from all directions, the spins always rotate in the same direction. So now there is another object, which is actually also very interesting, that Stewart Parking introduced Monday morning. It's the anti-skyrmion. So you see that the anti-skyrmion does not carry a charge of 1, it carries a charge of -1. And what is the difference between this object and this object is that actually when you go from the ferromagnetic background to the center of the skyrmion, depending on from where you start, you don't have the same rotational sense. On this axis, for example, you have what we call a right rotating spin structure, and on this one you have a left rotating spin structure. And so sometimes these objects are called also achiral skyrmions, because they don't show this unique rotational sense, which is shown here. And they have a charge here, -1. So now let's see how actually our spin glass behavior and how exchange, frustration of exchange interaction is actually very useful for us, because we can actually have both of them living at the same time in our simulation. So first let me introduce the technique that we use. We apply, so our playground first is actually the iron monolayer on iridium 111 surface. So why we use this system is because actually that's coming from an old paper here of Heinze and Blügel. It's a hard hat paper of 2009, where they look at the difference of energy between the ferromagnetic state and the antiferromagnetic state of an iron monolayer, so a single monolayer on top of different 4Ds and 5D substrate. And you see that as you move here from, let's say, the palladium substrate or the platinum substrate, which is very ferromagnetic, to the rhenium and the tungstenium, you switch from ferromagnetic ground state to antiferromagnetic ground state. And what is very interesting here, in order to have a spin glass, you need to have frustration. What is very interesting here is this region here, where the difference of energy between the ferromagnetic and the antiferromagnetic ground states is almost zero. So then you can see that you can grasp that there will be a lot of frustration. And actually, if you take iron on iridium 111, that was published in 2011, this is actually a nanoskyrmion lattice, which is shown here. So here the spins are actually rotating very fast. It's stabilized by even higher order exchange interaction, and this is a very, very complex spin texture. Now, this is when you use the substrate to modify here the ground state, but actually you can use the same kind of technique with an overlayer. And that's what happened here in this paper. So iron iridium 111 nanoskyrmion lattice ground state. Here you move to palladium iron iridium 111. So you have a palladium overlayer on top of an iron monolayer on top of an iridium 111 substrate. And you see that instead of having this ground state, which is very fast rotating spin texture, now you have a spin spiral. So this is a spin polarized STM measurement done in the group of Wiesenhanger in Hamburg, where you see that you have a succession of black, white stripes, which corresponds to the magnetization being up, down, depending on the direction of the tip. So if you change also this kind of stacking and you go to iron on rhenium 0001, you see that these two things are again changed, and then you have a nail state, which was also seen in a group of Roland Wiesenhanger in Hamburg. So how we understand here this change here is by calculating what we call the dispersion curve. So we use the code called FLEUR. It's a DFT code with a full linearized augmented plane wave approximation or basis set. So this code is actually very nice because you can calculate non-collinear magnetic textures, and you can also calculate what is called the spin spiral density waves. So DFT is actually very powerful at calculating homogeneous state. It can be collinear homogeneous states or non-collinear homogeneous states. And these spin spirals here are homogeneously rotating, and they are characterized by a propagation vector q. But here, the angle between the two nearest neighbor spins is actually constant. So if you do the Fourier transform of that, it's actually very well defined in reciprocal space, which is where we are doing our DFT calculations. So then when you have this information here of this energy as a function of the spin spiral vector q, then you can project this energy or parameterize an extended Heisenberg Hamiltonian where you have exchange interaction here, which is beyond first nearest neighbor. So this is an example that I'm showing here. This is the energy as a function of the spin spiral Q vector for 3 different systems. So you have iron and palladium 111, palladium, iron, iridium 111, and iron on iridium 111. And you see first, if you look at the iron and palladium 111, the energy is 0 at the ferromagnetic state, which corresponds to Q is equal to 0, and is maximum in this state, which is the antiferromagnetic null state, which is actually very high in energy, so high that we don't put it on this graph. And it means here that this antiferromagnetic state is unstable and the ground state here is ferromagnetic. If you go on the other side of the spectrum, you take iron on iridium 111. And here the situation is different. Instead of having a fast rise of the dispersion curve close to the gamma point, you have actually a very flat dispersion curve close to the gamma point. And this energy here is actually very small. So in that case, you have a very frustrated system, and you need to consider interaction, magnetic interaction beyond the second order, namely biquadratic and force-spin interaction to explain the ground state of the system. And you have the case in the middle here, which is palladium, iron, iridium 111, where you put one palladium overlayer on top of this system, and you see that the dispersion curve change quite dramatically, especially in this point. So here you destabilize the antiferromagnetic state. This energy now goes at around 110 millieV, but you keep some kind of frustration close to the gamma point here, so you have a very flat start of the dispersion curve, and you even have here a small minimum of the dispersion curve. So here you can say that this is actually showing that the ground state of the system is a non-collinear magnetic structure that we call a spin spiral, and this Q vector, the propagation vector Q, can be actually read here. So it has actually a period of 7 nanometers just coming by exchange interaction. So in order to model this kind of curve, you need to have interaction beyond first nearest neighbor. So what you can do after you have this dispersion curve is you can apply spin-orbit coupling. So I show you here a reminder of this energy as a function of Q, but this time we don't go to one edge of the boundary of the Brillouin zone. We rather go a left rotating or a right rotating spin spiral. The left rotating spin spiral is shown on the left here in the minus with a minus periodicity, and the right rotating spin spiral here is shown on the right with a plus periodicity. So you see that without spin-orbit coupling, this is the blue curve before, you find again this minimum, you have this frustration close to the gamma point, and these two minimum here are absolutely degenerated. They are exactly the same. Because without spin-orbit coupling, a right rotating spin spiral and a left rotating spin spiral are completely equivalent. If you consider only the exchange interaction, there is no chiral interaction into, which is embedded into the exchange interaction. So now if you turn on spin-orbit coupling, now the situation is different. You see that this left rotating spin spiral minimum is destabilized. This point here goes up, and now you stabilize a right rotating spin spiral. So it's really spin-orbit coupling which stabilize a right rotating spin spiral into palladium, iron, iridium. So DFT is a very nice technique because you can look very precisely at the energy, the origin of the energy. And so you can actually decompose the energies coming from the spin-orbit coupling depending on the layers. And that's what is shown here. So this is the variation of the spin-orbit coupling as a function of the spin spiral vector for a left rotating spin spiral and a right rotating spin spiral. And so here you see that the iron and the palladium, which are 3D and 4D metals, have actually a negligible contribution. Their contribution is mainly 0. You see that here is the black curve. The black curve is the contribution of the iridium. The iridium is a 5D, so you expect that a 5D element have a large spin-orbit coupling, and indeed, it's the main contribution to the total spin-orbit coupling here. So now if you take this curve, you can map it here into this Hamiltonian, which is the Dialoginski-Moria, which has here the Dialoginski-Moria vector. So now what you can see on top of that, so that's the chiral contribution to the SOC. There is a very small other contribution which is shown here. So here the blue point is being lifted up to the red point, to the red point here, and that corresponds to the magnetocrystalline anisotropy. So here with this calculation we have actually everything. you have the magnetocrystalline anisotropy, the exchange, and the DMI. So you are ready to set up your effective Hamiltonian, which contain all the ingredients. You plug on top of it the magnetic field, and then you can play with this with Monte Carlo or spin dynamic, depending on what you want to do. So in order to convince you that it works, this is, I think, very similar to the slide that Kirsten von Bergman shown a few days ago. So here is the palladium, iron, iridium with a spin spiral ground state. You apply an out-of-plane magnetic field. You see that you have this bubble being creating here, or this round contrast, as well with a stripe. You continue to increase. You have this hexagonal skyrmion lattice, and then you have isolated skyrmion. And now, this time, you have the Monte Carlo simulation, where all the parameters are obtained from DFT calculations. So left, you have the spin textures, and the right, you have the simulated spin polarized STM, so we can compare directly one-to-one these two things. So here you have indeed a spin spiral ground state, as I'd shown you before. You increase the magnetic field. You see that you have this kind of mixed state where you have these stripes here, which are elongated skyrmion or shortened spin spiral. And you have these small round objects here, which are actually skyrmions. And they are skyrmions within the spin spiral. You keep increasing, and you have an hexagonal lattice of skyrmions. So that is very nice. That works. No, this is at 0 temperature, and that's very, thank you for the transition, because now we could actually look at it at finite temperatures, and we could also look at the stability of these different objects, and that's exactly what is going to what I'm going to talk about. So there was a question for us when we started that, which was what actually is the advantage of taking the full dispersion curve? Why can we? Because at 0 temperature, normally close to the ground state, maybe there would be a set of parameters that could reproduce actually all the physical quantities without the need of this complex curve and this extended Heisenberg model. And so actually there was a paper of Niklas Roming in a group of Professor Wiesendanger who actually showed that he could fit a set of exchange interaction, anisotropy and DMI, and you could actually reproduce very well the 0 temperature phase diagram. So if you plot his coefficients here on top of the dispersion curve of these palladium, iron, iridium 111 system, this is what you get. This is the red curve here. So you see that close to the gamma point, the agreement is actually very good. But far from the gamma point, close to the edge of the Brillouin zone, there is a large difference of the null state. And so the idea was to look, is it actually physical? Does it have any consequence? And how to quantify it? How to quantify that? What we call frustration. So actually, we came with this J effective kind of concept, where we actually said, okay, let's fit our dispersion curve here only close to the gamma point, and let's get one parameter J effective that we call J effective, and let's see if it has any consequences. So on the barrier or temperature dependence. So we did it for these two systems here, palladium, iron, iridium 111. And you see that for the FCC palladium overlayer, the J effective, which is, for the HCP palladium overlayer, the J effective, which is obtained from DFT and from experiment, is actually very close. But as soon as you have a spin spiral ground state, like here, like in the FCC case, you have actually a negative J effective, because the dispersion curve has a negative curvature close to the gamma point. So actually, you end up with a system where you have palladium HCP on iron on iridium 111, when you have a J effective which is positive, which is not too far from the one obtained from experiments. And for FCC, you have one which is actually negative, which is very far from the one obtained from experiments. And as a comparison, I show you a system where you have absolutely no frustration. The cobalt platinum is a purely quadratic system. It's a strongly ferromagnet. Here, this is a purely quadratic curve. So you don't expect any difference here between J1 and J effective. And you see that our systems here are quite far from this case. So we decided now to classify no system as a function of J effective to see actually where we could find frustration. And so here is the palladium, HCP, iron on iridium 111. and the J effective is very close to the one obtained from experiments. And you have these two other systems, palladium, FCC, iron on iridium 111, and 2 palladium, iron, iridium 111, which have a negative J effective. So actually, here, if you look in this paper, there is the full graph that I don't want to comment today. And today, I want to focus on actually this system here, palladium, FCC on iridium 111. So I will focus on the ultra-thin film system. First consequence on the energy barrier. So in order to look for the energy barrier, we actually need to do a nudge elastic band on the sphere. So it's geodesic nudge elastic band, it's GNEB. And this is actually the paper where it is proposed first, the paper of Pavel Bessarab. And there is one group in Paris, the group of Stanislas Roard and the group of André Thiaville and Stanislas Roard, who applied this method on actually cobalt platinum for the first time. And so let's apply it on palladium, iron, iridium. Alors, this is a complex graph. There is a lot of information here. So here I show you the energy dispersion curve as a function of the spin spiral for palladium FCC on iron on iridium 111 and palladium HCP on iron on iridium 111. I show you also different way of modeling the important region of the dispersion curve, namely this minimum here, the minimum of the exchange and the DMI, which characterize actually the period of the spin spiral and which characterize the ground state. So actually, we find different set of effective J's depending on what we wanted to model. So here, I will only focus on the set where we actually want to model correctly the curvature of the minimum. So this is the red curve, the J effective for the FCC, and the J effective fit for the HCP. So on the right part, you have what we call the stability diagram at 0 Kelvin again, for the full DFT set of J, and for the J effective for palladium HCP and palladium FCC, so G defit and G effective. So you see that these two diagrams here for palladium HCP iron on iridium are actually pretty similar. So what you can say is that in this case, HCP, there is not so much difference between J effective and the full set of J obtained by DFT calculation. In the case of the palladium FCC, it's actually also the same. You have actually not so much difference here, except one line, which is here a line showing the stability of the anti-skyrmion. And that's quite interesting, because if you have frustration of exchange interaction, the anti-skyrmion might be stabilized. If you have only J effective, the anti-skyrmion is not stabilized at all. So now if you look not only at the ground state, we apply a magnetic field, and we look at a quantity such as the skyrmion radius, which characterize the skyrmion, you see that independent basically of all the parameters, you get something which is very similar. So it seems that if you stay close to the ground state, the frustration of exchange interaction and the J effective is actually not making any difference. Now, the question arises, what happened with the barriers? And that's what I show you here. Because if you think about it, when a skyrmion is collapsing, the angle between the spins are not small anymore. So you don't stay close here to this ground state, but you rather go here, you increase the angle between the spins, so you go higher in energy, and in these regions you have actually major differences between the full sets of DFT coefficients and J effective. So for HCP, palladium on iron on iridium 111, this is the barrier. You start with the skyrmion, you increase the energy as a function of the reaction coordinates, and then you fall into the ferromagnetic ground state. And so the barrier here is not so much difference. You maybe have 20 millieV difference, which is not that large. Now, if you look at the most frustrated system, which is palladium FCC on iron on iridium 111, in that case, you have a difference by almost a factor of 2 between the barrier, so with a full DFT coefficient and with only J effective. So if you plot now this energy, this barrier with a full set of DFT coefficient and just J effective as a function of magnetic field, you see that this actually behavior is constant in a whole range of magnetic field. So if you look at palladium FCC, if you have frustration of exchange, the energy barrier between the skyrmion and the ferromagnet is always higher than this orange curve, which is the J effective G for FCC palladium iron iridium. The difference here between the HCP stacking is much smaller than for the FCC stacking. So now the bonus of this frustration of exchange is that you actually stabilize the anti-skyrmion. So it's the same picture as I showed you before, and you see here that it has a very small energy barrier, so we can actually play around the anti-skyrmion in this system close to, for reasonable magnetic field. So here it's 4 Tesla. So now, this is, so for the barrier, actually having the full set of exchange interactions, coefficients coming from DFT is actually important. And now let's see, as a function of temperature, what it actually does. So here is the previous work that I selected, so it's non-exhaustive, on the temperature dependence on some system where you have skyrmions. So on top you have palladium iron iridium 111. So this is the first paper which published the phase diagram in 2016. And you see that here, as you increase the magnetic field here, the transition between the different regimes are perfectly perpendicular here to this critical temperature. That surprises us a lot, especially when we look at this kind of phase diagram for manganese silicon, where this actually feature is not found. You can have pocket, but here there is no 90-degree angle to be found between the phases. So this, you have that on that side, that's this work in comparison to the other phase diagram. And on the other side, if you look, you have actually a paper, which is now quite old, from 1989, which shows actually that you need creation of skyrmion and anti-skyrmion density pairs in order to have a phase transition. This is the work of Low and Dasgupta. And if you read, actually, if you look into this paper, which is one of our prediction, you can see that here, if you freeze, if you quench the magnetization in palladium FCC on iron on iridium 111, and you plot the topological charge density distribution, you see very funny features. You see round, red rounds, which corresponds to skyrmions here, and there are 7. And you see also a blue stripe, which are actually anti-skyrmion. They are, in that case, 4. And you see these triangular shapes here, which are actually higher order anti-skyrmion, and they are also, they have a very long lifetime, let's say, with the frustration of exchange interaction. And if you calculate the topological charge of these, of this supercell, you will get actually a topological charge of -1. So you will say that, okay, I should have here 1 anti-skyrmion into that. Although you have a lot of different type of particles. So it suggests that actually the skyrmion number is not an order parameter. So we cannot analyze the phase diagram with this quantity. So actually what we did, we actually use Monte Carlo simulation, which are adapted for spin glass behavior. Namely, we did parallel tempering Monte Carlo in order to obtain, let's say, order parameters with which we could characterize all the phases. So here is a reminder of the 0 Kelvin phase diagram for palladium iron iridium. You start spin spiral ground state, that is what we expect. Then you increase the magnetic field, you go into a skyrmion lattice, and then you go into a ferromagnetic state. Now, each of for different magnetic field, we actually started always with the ground state, and we did parallel tempering Monte Carlo. So here is an example. I show you only 4 curves for 4 different magnetic fields, depending on the ground state: 0 Tesla, 1 Tesla, 2 Tesla, 3 Tesla. You have 2 curves starting from the spin spiral ground state, 1 from the skyrmion lattice ground state, and 1 for the ferromagnetic ground state. And I plot the different order parameter that we first look at, namely the energy, the magnetization, and the topological charge. you see that in the energy, you have actually all the curves are on top of each other. If you look at the susceptibility or the heat capacity, you see that you have a peak here, which corresponds to the critical temperature, and you can define a boundary between a disordered and the ordered phase. This allows us to set up these bars here. From this gray shaded area, we use it to define the right side. So now if you look at the magnetization for the 4 different cases, you see that it's more complicated. You have actually some features here at low temperature. And if you look at the magnetic susceptibility, you see that you have actually a sharp peak here appearing. So between these 2 bars in this shaded area, there is something going on which we need to analyze. The topological charge gives you somehow a clue, which is that here, if you go through if you increase the temperature and you look at the topological charge, you see that you have a sharp increase of the topological charge in this shaded area. However, since I told you the topological charge does not mean anything, we can have whatever skyrmion and anti-skyrmion into the system. So actually, it is much better to look at the skyrmion and anti-skyrmion pair creation, which we call Q plus Q minus. And this is what is shown here on the left. So this is the Q plus Q minus as a function of temperature. And here you have the susceptibility of the Q plus Q minus quantity. So the susceptibility of the creation of skyrmion and anti-skyrmion. And that's the first surprise here. You see that although you have DMI actually included, both Q plus and Q minus are actually always increasing as a function of temperature. And actually, when you go in this shaded region here, these 2 curves starts to split. And you have a difference in the creation of Q plus and Q minus. If you look at the susceptibility, you indeed have a sharp peak here at low temperature, and you have a broad peak here at high temperature, which was also seen with Dasgupta. And this actually quantity, if you record the position of the peak, of the 2 peaks, you actually can define the transition region between all the different phases with, let's say, a nice precision. So here you have the pocket of the spin spiral. You see that now the TC is not constant if you compare from this phase diagram already published. You see that actually the TC, when you have a spin spiral ground state, decreases as a function of magnetic field. You have here the pocket of the skyrmion lattice. And then you have this critical temperature here increases again when you are in the ferromagnetic state. See that in this region here, in the colored region, the topological charge is actually almost constant. So as soon as you are here, you don't change anymore the number of skyrmions. When you change here into this gray shaded area, your number of skyrmions can change, and as you increase the temperature, of course, you start to have less and less skyrmions. So now if you plot this information, which is this one, the skyrmion and anti-skyrmion density as a function of temperature, you get the graph on the right, which I show here. So you see that at low temperature, unless you are in the skyrmion lattice phase, the Q plus and Q minus are actually on top of each other. They start to split when you go in this gray region, and then they are on top of each other again. So which means that now creating or deleting topological charge it seems to be that you create actually more skyrmion than anti-skyrmion. And then you freeze them when you go back in low temperature. So in order to show that, to have an idea of what's going on, I show you here the topological charge density distribution at 2 different temperatures for B equal 2 Tesla. On the left part, you are at very low temperature, which is around 1 Kelvin. You see that you are in a skyrmion lattice. It's a 4x4. As the time of the simulation goes on, you see that the topological charge stays absolutely located around these skyrmionic or these skyrmions here. And actually, there is not much going on. So you even have the impression that the movie is not running. However, if you start to go in this region here, so at the border between the gray shaded area and the red area, you see that actually you have a lot of motion of your spin texture here, and you cannot correlate anymore the topological charge density to the spin texture. You can even create more skyrmions than in a skyrmion lattice, so you can pass to Q equals 17, and you can also decrease the number of skyrmions. And you see that it looks almost like a fluid, and if you look carefully into it, you will see that although here you should have only skyrmion, you have actually some blue dots appearing and disappearing all the time. Shows that here it's like vaporization of topological charge, or it's like a topological charge liquid or something. And so this brings me to my conclusion. So overall, we can explain the occurrence of skyrmions based on density functional theory. We can tune their property based on exchange and DMI, especially with the frustration. The magnetic frustration, especially from the exchange interaction, can actually enhance stability. It's not only something which destroys the skyrmions. We can do spin dynamics at Monte Carlo based on these DFT parameters with long-range exchange interaction in a multi-layer-like geometry also. So yes, and with that, I would like to thank you for your attention. Thanks.